Okay, so here's Misha Bialy, former student of Boris Kanevsky, and he'll talk about rigidity of Mather beta functions for convex billiards.
Okay. Yes, first of all, thanks for inviting me here. It's a really special event and very emotional in a sense. So, I shall start. My first slide is, well, right. Yesterday was maybe. I'm sorry. That's a printing. Oh, maybe no. Let's see. No.
The bottom was with the clicker.
Yeah.
That's it. Now it works?
Yeah. Okay. So this slide it's called curriculum vitae. So only some personal remarks, and then I will pass to the talk. So Boris Ilyich was our teacher in Moscow Mathematical School number 2 50 years ago. Together with Valery Senderov and Bella Abramovna, they prepared Jewish students to solve coffins for entering exams to MGU. They distributed pamiyatka for the Jews entering exam to Michmat. In summer 1979, my mother, Judith Ratner, organized a press conference in Moscow for foreign accredited journalists where the first version of intellectual genocide was presented. When Boris and Valery were arrested in 1982, our parents, me and Lenya Polterovich, decided to send us to Gelendzhik, such a resort town on Black Sea. When we returned back to Moscow, we got immediately the summons to Lubyanka, 3 of us. And also, in my personal life, in 1986, a day before Lag BaOmer, Masha, my wife now, told me that she always had an idea to have chuppah on Lag BaOmer. And my parents that time were in Klin, where Boris and Lisa resided after Boris' exile. There was no way to notify them. Finally, somebody passed them my invitation. They arrived very last moment, bringing bouquet from Boris and Lisa. So, do you remember? So such a such a strange thing. Yeah. So it was interesting place, Kli. Right. Okay. So let me pass to my talk. So it's geometry talk. So we're supposed to be quite elementary. So you see here the idea. So the problem which I'm going to discuss is the following variational problem. So you are given, suppose you are given a convex closed curve, simple, and of positive curvature in the plane, and you consider polygons either inscribed or circumscribed, and you want to extremize certain parameters like perimeter or area of this polygon. So they are constrained to be inscribed or circumscribed, and here are the results. So it was first result was proved by Schneider in Ralph Schneider 71, and then this last theorem belongs to Ernst Sass, 1939. So this theorem tells that suppose you are given a inscribed polygon of maximal perimeter inside this curve gamma, then the perimeter satisfies the following inequality. Pn is greater than length gamma of this number. So how can...
This one is not so good per se.
No. Well, but it's true well, not in his paper, not. So this inequality should be understood in the following way. You need to normalize, divide by length gamma, and then you say this normalized perimeter is greater than the perimeter of the polygon in the disk, because this number is the maximal perimeter of the polygon n-gon in the disk. So theorem B, yeah, and equality holds only when gamma is a disk, and this equality case were considered by other people. Schneider couldn't prove this. Next is this theorem also belongs to Schneider. It consider polygon of minimal perimeter, but circumscribed polygon, and then Qn is less than this number. And again, if you normalize by length gamma, then this number is just the minimal perimeter of circumscribed polygon for the disk. And this theorem C, this consider polygon which is inscribed of maximal area, now not perimeter but area, and then this inequality holds. So these three kind of geometric inequalities. And now notice that the fourth theorem, which would be very natural here, it's areas of circumscribed polygon is missing here, and for good reason, as we shall see. So now let me say how this is related to billiards. So in fact, these results are related to four type of billiards. Namely, it's very well known that if you have a periodic trajectory, trajectory of the billiard in the plane, then it maximizes the perimeter. So this gives a relation with the previous inequalities, which I showed on the previous slide. So what are the billiards? So this one is called Birkhoff billiard. It's usual billiard where you travel along the line, you hit the boundary, and then you reflect with the usual rule, angle of incidence equals angle of reflection. This is called Birkhoff billiard table. Now the second billiard is called outer billiard. This here the game plays outside the curve, and the rule is the following: you have a point, and in order to get the next point, you need to draw a tangent line agreeing with the positive. So in a positive direction of the curve, you choose counterclockwise, say, orientation of the curve. And so if you have a point, you draw this tangent line, and then you travel the same distance. So you need the tangency to be the middle point of this segment AT. So in such a case, you can continue next, and so on and so forth. This billiard is very remarkable. It was invented by Bernard Neumann, and probably even earlier by Mahlon Day, was such a mathematician. And later on, Jürgen Moser popularized this model as a toy model for celestial mechanics, and proved very remarkable KM type results for this billiard. Now, the third billiard is called symplectic billiard. The rule here, the game here is the rule is the following: you have a point x and next point x prime. And in order to have x double prime, you draw a tangent line here, and travel parallel to this, and then you hit this X double dot and so on. This one was invented by Serежа Tabachnikov, who is present here, and the orbits. So the fourth billiard is this one. It's called outer length billiard. It's most complicated, most complicatedly defined. So if you have a if you have a curve gamma and you draw a circle which is tangent to this gamma, then there are two tangents, mutual tangent, joint tangents of this circle and omega, and then you have these 2 points, and then you say that this one they are in correspondence. So the image of this M0 is TM0, and so on, and you repeat. So you get another point, you draw a circle, and then tangent, and so on. So it's called outer length billiard. Why are they so? Why these 4 type billiards are so naturally related to what I showed before? And the reason is the following: that if you have an orbit of the reason is variational principle for billiard. Each time you have a billiard, it gives you a certain variational principle, and this variational principle coincides with these theorems, with these variational problems of theorems A, B, and C, and namely, for usual Birkhoff billiard, you want to extremize or maximize the perimeter. For outer billiard, you want to minimize the area properly defined. So for example, you can choose an origin inside gamma, and then you measure the if you have a polygon, then forget about origin. If you have a polygon, then you want to minimize the area covered by this polygon. This will give you an orbit of outer billiard. And now here, this is also here. Area is variational principle. Area gives you a variational principle, but from inside. So you want to maximize area for inscribed polygons. And the last billiard is you want to minimize perimeter, minimize travel by this periodic orbit. So now small remark that these 2 billiards, they exist in the realm of Euclidean geometry, and these 2 are kind of affine geometry, because area, if you make equifine transformation of the plane, it travels the same orbit. So now let me say a couple of words about billiards as an advertisement. So it was well, as far as I know, it was Birkhoff who considered convex billiard, and he wrote highly typical illuminating model. So he considered convex billiards as a kind of toy model for geodesic flows or Hamiltonian systems, and this was his idea to check things. Probably real things can be discovered first for convex billiards, and indeed, as we know nowadays, many theorems started like this. Next was Anatoly Katok. He used to say that billiard table is a playground for mathematicians. Well, and this he wrote, this should be understood as proving ground. Various questions, conjectures, math solutions in theory of dynamical systems are tested on various types of billiard problems. Okay, so for today, as I said, I have these 4 billiards to discuss. So first was Bergov, Mahlon Day. This Mahlon is a Jewish name, by the way. Yeah, so instead of root, he was well, I don't know, was he Jewish or not, but it's a really strange name because Mahlon, the illness, Mila Machala. Well, I don't know. So next was Neumann, and then Jürgen Moser, as I said. Symplectic billiards were invented in Albert Sabachnikov, and outer length also Albert Sabachnikov. Well, but there are many others, for example, Minkowski billiard, which plays very important roles in symplectic geometry nowadays. Magnetic billiards from physics, Robnik, Berry, wire billiards. Sinai was a kind of father of modern era of billiards, Sinai Bunimovich, and so on. Okay. So let me explain what is beta function, how it's related. So suppose you have an area preserving twist map of the cylinder. So when I say positive twist, this means that it tilts the positive vertical direction to the right. And for example, all these billiards which I explained, they are examples of this twist map. So Mather beta function was invented by John Mather, and it assigns to every rotation number rho the average action of a minimal trajectory with this rotation number. So this maybe looks very abstract to you, but for billiards, it's really very simple to explain. So what is for billiards? So suppose I have rotation number m over n, and I have a Birkhoff billiard, then I consider the polygon, which is a closed trajectory of this Birkhoff billiard, making m rotation before closing. And so what we can count is maximal perimeter of this inscribed polygon and divide by the number of vertices of impacts. So if you have outer billiard, then you just count minimal area covered by this polygon and divides by number of vertices. And for symplectic, it's maximal area, and it's minus sign here and here needed in order to have positive twist map to fit this Aubry-Mather theory. And for outer length billiard, you compute minimal perimeter of the circumscribed polygon and divides by the number of vertices. So, usually, general idea is to compute average action of a minimal trajectory. So you have a trajectory, say periodic trajectory, and you compute the action and divide by number n. And that's what is remarkable that this beta function is.
How this function is defined for irrational values?
Very good question. Thank you. So, for example, it will be clear from here. So let me not enter the details. It can be done. So Mather proved that it's strictly continuous, and therefore, for irrational, you just define it by continuity. For example, you can think about continuity argument. Okay. So and moreover, what Mather understood that this function beta is always differentiable at any irrational number. However, if you want, if you have a rational rotation number, then beta is differentiable if and only if there is an invariant curve consisting of periodic orbits with this rotation number. So this invariant curve must be filled by periodic orbits. Okay, so not separatrices, but really genuine invariant curve with periodic points. Okay, so this is the background in a sense. So what what are the relatives of this beta function? So it's not a kind of absolutely new, because it was considered in Riemannian geometry. The counterpart of this function is what is called Mark length spectrum. For example, if you have a surface, then you can assign to every homotopy class the length of minimal geodesic. So you get a
Homotopy class of a curve.
of a curve, right? But well, in geometric measure theory there are more complicated objects, not necessarily curves, but here we'll stick to the curves. No, and also I'm not going to discuss this, just to have an idea what it is about. It turns out that by this Mark length spectrum, it somehow encodes in several cases the geometry of the surface. For example, if it is negatively curved, famous results by these people, and nowadays there are new. You can recover by Mark length spectrum. You can recover Riemannian metric on a negatively curved surface. However, for Riemannian tori, this Mark length spectrum not necessarily recovers, because if you have metrics with big bumps, then minimal trajectories do not travel to this bump. It's kind of not economic, and therefore you cannot recover this Riemannian metrics. However, flat tori can be recovered, as was shown by Banger. And it is a big question in this theory if it's possible to recover Riemannian tori close to flat one, maybe for integrable metrics and so on. But it's not this discussion is just to give you an idea what is beta function is, because it's completely analogous to this Mark length spectrum. All right, so what it turns out that these theorems A, B, C, which I mentioned before, they are in fact they can be understood as a certain isoperimetric inequality for this beta function of the billiard. So this was found recently in our joint paper with these Italian guys, and remarkably, it can be proved for 3 out of 4. So one billiard is a kind of this is an exceptional in this story. So what is the theory? Suppose we have a convex billiard table. Gamma is the boundary curve, is assumed to be C2 smooth, positive curvature. And consider this beta function, which I explained. This is a function which assigns to a rotation number minimal action of the billiard trajectory with this rotation number, and then this function satisfies the following inequality. So here the billiard can be Birkhoff, symplectic, or outer length, or this sometimes called fourth. And the following inequality holds that the beta function of this billiard at rho is less or equal than beta of the disk. And here, disk must have the same boundary length as gamma, in case we are talking about Euclidean geometry, that is Birkhoff and outer length billiard. But if we are talking about symplectic billiard, then this disk must be of the same area as omega. So this result encodes all 3 inequalities which I explained at the very beginning, A, B, C.
Excuse me, was it equal in ABC that the curve is convex?
Yes, it
Oh, it
was,
was
yes,
required.
it
Okay.
was
Like
convex.
some zones. Okay.
Yeah, sure. Yeah, and I think all these guys required also positive curvature. I mean, not strictly convex, not only convex. So, and what interesting is that now we can explain what are equality cases here, because this was the kind of issue in Schneider approach, and here, sorry, so it's not a Jewish. I'm sorry, pointer. It's not a Jewish pointer. Well, so. So the equality case in theorem one, so one shall say the following: they are related to the so-called Birkhoff billiard tables, Gutkin billiard tables. What are they? So suppose you have a billiard, then you ask Gutkin asked if there are invariant curves such that along this curve the reflection happens with a constant rotation number pi. With a constant angle pi rho. And it turns out, and Gutkin discovered that these billiard tables indeed exist, and for this purpose, rho must be a solution of this transcendental equation. So for some k equals 3. So again, what was Gutkin, to draw at least something? So Gutkin asked, is it possible to have an invariant curve such that this angle all the time is the same? And this is possible, in fact, except not only for this, of course. Yeah. So, and here is this theorem 2. It says if for some rotation number rho the equality in theorem 1 holds, then so if it's for rational equality holds, then it's necessarily ellipse or disk. Ellipse for symplectic billiard and disk for Euclidean billiards. But the interesting story when rho is not rational, in this case, the claim is that theorem 1 holds for Birkhoff billiard if and only if omega is Gutkin billiard table, and this can be precisely described. It was described by Gutkin. Okay, so and as I said, that for if rho is irrational, but the billiard is some other billiard, not Birkhoff, then only trivial ellipses or disks satisfy the equality case. Okay, so now let me. How much time?
20 more minutes. Some variables.
How?
20 more minutes. 20 more minutes.
Okay, so probably I will. So let me explain now some facts which are kind of well, you can think it's a kind of introduction. So suppose you have a space of lines, you have space of oriented lines in the plane, then you have two ways to think about coordinates on this, to introduce symplectic structure on the space of lines. So one way is the way which was used by Birkhoff. It's the following: in order to consider lines intersecting your curve gamma, you assign to every line the point where it intersects gamma, where it enters gamma, and call this S. It's you measure some distance, some length, arc length along the curve, and this angle cosine delta. Turns out that these are symplectic coordinates. That is, you take omega, which is differential of this form, cosine delta ds. It's this two form. This is the symplectic structure, and this structure is preserved by the reflections for Birkhoff billiard. But there is another way to describe this the same structure, and it's the following way. It doesn't matter what is the curve gamma, you can say I take a line and then I take the angle of the normal. It's not normal here, but well, this is supposed to be normal to this line. You measure this angle phi and the sine distance to this line. So you get two coordinates p and phi, and then you have symplectic structure written in these coordinates omega dp d phi is the same as here. And so it is invariant and can be used. And then you may ask, okay, I have a symplectic map that is billiard map of the cylinder. It preserves symplectic structure. It was known to Bergov. And then what is generating function? That is, you are looking for, you take this one form, cosine delta ds, and the differential is omega. You ask what is the what is this difference to be differential of some function, and this function is called generating function. So you take this difference and you look for differential of a function of two variables, s and s1. This is s, this is s1, delta 1, and so you understand that delta must be partial with respect to s equals this minus cosinus, this partial cosinus delta 1, and so you have this symplectic map, and this is L is just, it turns out that L is just the distance between these two successive points, gamma s1, and this is exactly the approach used by Bergov. And now what's now with the second set of coordinates? If you have these coordinates p and phi, then you take this primitive form p d phi, and you ask what's the difference? What is the differential of which function it is? And it turns out it was discovered together with Mironov that for Bergov billiard, generating function can be written in such a simple formula. So you have a twice h of psi. H is called support function. Sinus delta. Psi is the average of phi plus phi 1 over 2, and delta is the angle phi 1 minus phi over 2. And so it turns out that if you differentiate s with respect to phi 1, you get p1, and if with respect to phi, you get p. So this is a kind of non-standard generating function for Bergov billiard table. Okay, and why it's so nice? Because I give only one proof. Okay, so I want to give you one proof, and very short. So suppose you have so this proof of theorem 1 for Bergov billiard. So I want to show that Mather beta function satisfies isoperimetric inequality. So take any rational rotation number and consider such a configuration of angles which is equispaced. You see, I fixed Mn and I consider the configuration phi k, which starts with certain phi, and it is equispaced with respect to phi. And then I want to compute the action of this configuration. So this action, average action, so a phi over n, and what is action? It's just you take sum of generating functions computed phi k plus 1, divide by n, minus again because it's positive to symmetry, and so on. So you plug all this inside here, and since angle is constant, difference of the angle is constant, you get this number sinus here, and this is h under the sum, and since this is action of this corresponding to this configuration, and since beta is minimal action, you have an inequality. This must be greater or equal than beta gamma corresponding to this mm. Now integrate this formula with respect to initial phase phi and divide and average. And so you get, this is the constant, it's here, and then you compute integral of this h, and you use that in integral geometry, well known, integral of support function is the length. So you compute the average, it's this number, it's greater or equal than beta gamma, and then you are done. So this inequality is very natural if you use this non-standard generating function. Here is Gutkin. He passed away a couple of years ago. Zhenya Gutkin. Yeah. So what he did, he considered, as I said, this Gutkin billiard table. He was here several times in Israel. Yeah. So if the angle is rational, then the only Gutkin billiard table must be disk. That is, this equation which I showed you before, it cannot have rational tangents k rho equals k tangents rho, cannot have rational solutions. It was proved by Van Sir. However, for irrational, it can be, such table can exist and they can be described. So how it's related to Gutkin billiard? Because you see in my previous proof, if we come back here, if you have equality, this means that you have a configuration which is genuine orbit, and then the reflection angle is constant, and therefore equality in this isoperimetric inequality for beta function can happen only for the case of Gutkin billiards. So and now let me So now let me explain that, in fact, why this outer billiard. Remember, outer billiard was a billiard where we play a billiard outside, and each time we are tangent in the middle, like this. And why it's exceptional? So let me explain this. So in fact, if I would like to formulate isoperimetric inequality for outer billiard, I would need to have the following result. So suppose I'm given this domain omega, strictly convex, boundary gamma, and then the question which I'm asking is it true that beta computed at rho divided by area, normalized by area, is less or equal than beta computed at rho normalized by the area of the disk? So, and here is the amazing fact. Suppose gamma is radon curve. I shall explain what it is in a moment. So maybe now, let me explain what is radon. Here we are. So radon curve, this called radon curve, is the following thing. Suppose you have a convex norm, norm in R2, yeah, and this is unit ball of this norm. And suppose you have two vectors, x and y, and I want to say what does it mean x is orthogonal to y. It's called Birkhoff orthogonality. X is said to be orthogonal to y if y is parallel to this tangent line at x. Now, this relation is not necessarily symmetric. If it is symmetric, the norm is called radon norm, and the curve is called radon curve. So it can be shown that equivalent definition is that if you play outer billiard around this curve, then you have a family of 4 periodic orbits. of period 4? No, because this will be tangent here and so on, and you see this orbit. So so coming back, yeah, no, not back. Yeah. So suppose I'm given such a curve, which is Radon curve, so it's centrally symmetric, and it is such that outer billiard map has invariant curve of 4 periodic orbits. Each of these orbits form a circumscribed parallelogram of minimal area. Rescaling, we can assume this area to be 4. Just rescale this. Okay. So in this case, we have area 4. So if we want to compute beta function, I need to average divide by 4. Therefore, area divided by 4 is 1. And the same is for unit disk. If you consider 4 periodic orbits, it covers area 4. You divide, you get 1. So you have consider such a Radon curve, and if you have a Radon curve, another property of this curve is that a polar dual to this curve rotated by pi over 2 is coincides with gamma. So if you take polar duality and rotate by pi over 2, that is, in fact, this is the duality not with respect to Euclidean scalar product, but rather symplectic form in the plane. So Radon, if you have Radon curve, then gamma and gamma dual rotated by pi over 2 coincide. And therefore, there is such an equality in affine geometry. It's called Blyashky-Santalo inequality. It tells you that product for any convex curve, product of area and area dual and of the dual is smaller than pi squared. So in our case, our curve is Radon, therefore area omega and omega dual the same, and therefore we get this area omega is less or equal than pi. So as a conclusion, if we have a Radon curve normalized to have these 4 periodic orbits of area 4, then we have area omega is less than pi or equal. And this is the opposite of this inequality. This completely opposite to the inequality which I addressed, right? So in other words, we have the following theorem. Suppose gamma is centrally symmetric curve, then this inequality holds for any such a curve, and equality only for ellipses. So we see a strange thing. This isoprometric inequality holds true for 3 billiards, but not for the 4th. And also, if you have rotation number 1 over 3, then it's also not true. So probably I'll skip this slide. It was here also some inequality by Blyashky is used of area of inscribed triangle. Okay, so let me. Yeah. So, but you might think that it's always the reverse, and the answer is no. So there are curves which this inequality, isoprometric inequality, holds as was our first guess. So take a disk. Yeah, so in a sense, in these Radon and triangle, important point is that there is an invariant curve of 4 and 3 periodic orbits. If you drop this assumption, you can have the kind of correct inequality. So take a disk and squeeze it. So take a disk such that the area of this square is 4, say, for example, and then squeeze it a bit in such a way that the area of this curve remains the same as it was, the same as area of the disk, but definitely you decreased the area, right? in this case. So in some sense, situation, well, not clear to me what's indeed the correct statement. Probably it could be that the correct conjecture is that if there is an invariant curve of any rotation number, then probably the reversed inequality holds. If not, no. Yes. So Serежа, that's it. So therefore, we come to the last slide, which is many happy returns to Boris Ilyich. Thank you.
Well, we are left with maybe 2 minutes for questions. Are there?
So there is no CRMT, right?
That's the message. Yes.
Theorem
And it's
is,
kind of-
there is no such thing.
Kind of mysterious. Yeah. Well, yeah. So I couldn't continue. I'm over time.
So it's really very interesting, right? This separation of
Yeah. So it's
into class.
yeah. So in fact, I think this outer billiard is a kind of more flexible thing. Yeah.
Do I understand properly that all these examples of billiards, yeah, they have some symplectic language to talk about?
Yes. Exactly.
And
They have sort of rational principle, and this rational principle leads to symplectic twist map.
yeah, and your theorem 1 is just theorem A, B, and C together, right?
Right.
But you don't have proof that it's not just considering separate cases. Somehow
We did this. So first of all, you can
I mean,
we reprove these results using generating functions, as I have shown for Birgov billiard.
Mhm.
So our approach is to use non-standard generating functions in order to prove, and then it's one line.
So you
You
can.
may suggest that you continue this discussion.
Yeah, sure.
Okay.
Yeah, sure.
Oh,
Right.
So thank you, Mr. We are a little bit over time.
Я хочу задать
So, Rania,
То есть,
are you ready?
значит, ты можешь переформулировать это так, что какая не верна для... Ну, если ты можешь это формулировать... Это вопрос